Kalavana from the University of Moroto, Sri Lanka. Today, I will be presenting on emulating a computing grid in a local environment for feature evaluation, which include both a research component and an implementation. We conducted this research in collaboration with CERN in Switzerland. Moving on. So let's start with what grid computing is. Grid computing is a type of distributed computing where multiple computers, often located in different places, work together to solve complex tasks. They do this by combining their computational power and resources. So one of the main advantages is that they provide immense computational power in a cost-effective and accessible way. This makes grid computing a great alternative for general users, especially when compared to supercomputers, which are often expensive and not easy to access. Now, let's see what are the applications of computing grids. First, in scientific research, it facilitates a large-scale simulations and data analysis, which are essential for making breakthroughs in many fields. As we will see a bit later, our research is also focused on such application. Next, in medical imaging, grid computing supports advanced imaging techniques like MRI and CT scans, which help provide faster and more accurate diagnosis. Then, in financial modeling, grid computing accelerates complex simulations and risk assessments, which are crucial for better decision making in the finance industry. Finally, in disaster recovery, grid computing ensures reliable backups and enables faster recovery of critical systems, helping to minimize downtime during emergencies. Next, as our topic suggests, we will be talking about feature evaluation. So let's first clarify what we mean by features in this context. Features refer to new functionalities, optimizations, or enhancements in the software and infrastructure of grid computing systems. Examples of these features include workload management processes, monitoring tools, and other similar improvements. Now, let's look at why evaluating features on computing grids is challenging. Grid systems consist of multiple distributed components and services, making feature testing complex and resource intensive. While there are existing grid simulations for evaluation, they also consume substantial resources and take a significant amount of time. Unfortunately, it is not practical for an individual developer with an average PC to use those simulations efficiently. Typically, in grid systems, testing starts with production deployment on a single site, then expands to few sites and continues to grow. However, this process comes with limitations, disrupt operations, impact performance, and lead to downtime. Most importantly, it also requires significant amount of time. So this is why our research and development is important in this context. Now let's talk about local grid emulation as a solution. This provides a controlled environment to test features safely without impacting the live system and emulates grid behavior using minimal resources and significantly reduces testing time. Most importantly, even individual developers can set up grid emulation on their PCs and perform the necessary testing with this before deploying features to the production grid. So we can get rid of the limitations mentioned in the previous slide. Now, let's focus on the suggested methodology. We are working with a computing grid and a specific feature on that grid. The goal is to ensure this feature continues to work as expected even when modified or within a minimal local environment. The first step is to study the system and the feature itself. We identify and select only the necessary components and services of the grid that need to be emulated in the local environment for evaluating this specific feature. Unlike a full grid simulation, we don't need to build the entire grid locally. Instead, we focus only on the components associated with the feature we are testing. This significantly reduces resource usage and effort. Next, we consider how to emulate these components locally. While virtual machines are an option, using containers is a more lightweight approach. Containers require fewer resources and less time to set up. Of course, we will need some automation, but the reduced resource usage makes containers the best choice. Tools like Docker or Singularity can be used for this purpose. Now that we have the container set up, let's see how to evaluate features. Of course, developers can manually test the feature using the local setup by executing and observing terminal commands, but this process is cumbersome and time consuming. Additionally, manual testing is dependent on the tester. So the solution is to create a test suite. Now, this may sound simple, but not when dealing with the computing grid, because here we are considering multiple containers running simultaneously, each carrying out operations concurrently. So developing such a test suite takes a significant effort. However, once in place, this will save a lot of time for developers during testing or feature evaluation. So focusing on the test, first we will have test to ensure the emulated grid environment is set up correctly. Then we will conduct feature testing by running the feature on the grid and checking the outputs or logs. Additionally, we can include tests that go through the logs generated by the containers to ensure everything is functioning as expected. Now, with the above mentioned steps, we have a local grid emulation, but there's still a room for update. Suppose a developer needs to use this setup. They would have to go through all the documentation to set up and run the test suite. What if we could automate this? Imagine being able to start the local setup, run the test and show the result with just one command. That is exactly what we are aiming for here. The ultimate goal here is to create a CI/CD pipelines and deploy them for the feature code repositories. So whenever feature is modified, these CI/CD pipelines will be triggered and handle everything from starting the setup to running the test. In essence, we are automating the entire process. So that was the research component. Now let's quickly go through the implementation component. We applied the suggested methodology and successfully implemented the grid emulation for feature testing. Our focus was on the CERN Alice grid, specifically its job submission functionality, which we aim to evaluate. The goal was to build a local setup that emulates the Alice grid, allowing us to evaluate its job submission feature with minimal resources, effort, and reduced time. So as mentioned earlier, we are focusing on evaluating the job submission feature of the CERN Alice grid. Now, CERN is the European Organization for Nuclear Physics, and CERN Alice Computing Grid provides the massive computational power required for conducting complex calculations in high energy physics and large scale data analysis for the Alice experiment. JLN is the framework responsible for workload management, including job submission within the Alice grid. JLN is a very large Java code base. So following the methodology, the first step is to identify the components associated with JLN as its feature we need to evaluate. These components are JCentral, computing elements, storage elements, batch queues, and worker nodes. We don't need to focus on the specific functions of this component for this presentation, but it is important to note that JLN code runs on most of these components, and when all these components work together as a whole, they emulate the job submission process of the Alice grid. JLN replica or JLN setup. It is a multi-container setup where each container represents a different component. This setup was implemented by CERN a few years back, but due to its limitations, it was rarely used. Since this setup aligns well with our methodology, we decided to use it as our starting point for our implementation. Our goal was to modify this setup, addressing its limitations and ensuring a smooth evaluation of JLN as outlined in the methodology. Now, if you are interested, here is the architecture diagram of the existing JLN setup. Each gray box here represents a container. On the left, we have JCentral, which acts as the central server. It handles authentication and job management. Inside JCentral, there are three components: LDAP, MySQL database, and another database called TaskQueue. Here, LDAP stores user credential data, MySQL database stores job metadata, and TaskQueue stores submitted job data for the central server. So when a user submits a job to the central server, the computing element or CE detects it. Then it creates a job description document and submits it to the batch queue. Then the batch queue is responsible for running the necessary job on a worker node. Finally, there's the storage element. It is used to store input and output data related to the jobs. So we need to have containers for each of these elements and elements to create the local grid emulation for the Alice grid to evaluate the JLN feature. Continuing with the implementation, let's take a look at the JLN setup test suite. We used bash scripting to write the test script because it is simpler to communicate with containers and can run in Linux environments without dependencies, but we can use any scripting language as we need here. First, we have test to verify the host system prerequisites such as ensuring that Java, Python, Docker, and other necessary tools are installed. Then we have component-wise tests that verify the functionality of each container. These tests ensure that all necessary dependencies are installed and that required services are running smoothly. Finally, we also have tests that verify the job submission flow of the JLN middleware and tests that examine the logs generated by key containers, including JCentral, computing element, and storage element. As mentioned earlier, we can set up CI/CD pipelines for complete automation. In this case, we have 3 CI/CD pipelines, and we will take a look at them in the next slide. In summary, these pipelines ensure that all modifications to JLN are working as expected without requiring manual intervention. So these are the flowcharts for the CI/CD pipelines. All of these work in a similar manner with a few differences depending on the objective. The two CI/CD pipelines on the left are triggered when a code change happens in the JLN and JLN setup repositories. The one on the right is triggered by a cron job running weekly, which builds new container images for the JLN setup containers based on the latest updates. All of these pipelines clone the necessary repositories, start the container setup, run the test, check for critical errors, and if there are any errors, they display the test results. Otherwise, they will update the container images. This is how the final architecture looks after our improvements. The purple boxes you see here represent the enhancements we have made. Now users can use automated batch script to simplify the process. These scripts can invoke Docker Compose to start the emulated setup, run the test suite, and retrieve the test run results automatically. This streamlines the workflow significantly, making it much easier and faster for developers to evaluate features. Finally, let's focus on the evaluation. This is a comparison between the existing setup of version 1 and the enhanced setup of version 2. As we can see, the version 2 setup introduces 3 new functionalities that are essential for carrying out the suggested methodology. They are test suite to assess features, automated scripts for setup and testing, and CI/CD pipelines. If we focus on execution times, the new version or version 2 takes around 108 minutes. The numbers for version 1 mentioned left are based on an experienced developer using the JLN replica. So for others, these times may be even higher. However, the execution time for version 2 will remain approximately the same for all the developers. So as we can see, version 2 is a significant enhancement compared to the version 1. So in conclusion, the generalized methodology can be applied to computing grids to locally emulate them for feature evaluation, providing a controlled environment for testing or feature evaluation. Developers and scientists can use the test suite to check their implementations before pushing them to the production. Additionally, the CI/CD pipeline automates the task, streamlining the process of building and pushing the container images. Yeah. So this is the end of our presentation. Thank you for your time and attention.